Good morning, everyone, and thank you very much for joining us for today's webinar, A Thermal Bridge Too Far. My name is Shalika Sivathasan, and I am the Administrative Assistant in the Continuing Education Department at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and who are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we begin, I would like to share some important information to ensure an effective and professional webinar experience. Please be informed that this session is being recorded for quality and educational purposes. For accessibility, we provide automated closed captioning service available in multiple languages to accommodate the needs of our diverse audience. In order to maintain a stable internet connection, we have muted all participant microphones and disabled video feeds. Kindly note the chat function has also been deactivated. However, we do highly encourage engagement through our Q&A window, which you will find at the bottom of your screen. Feel free to submit any questions that you may have for our speaker there, and questions will be answered during the designated question and answer period at the end of the presentation. For those seeking continuing education learning hours, please note that attendance is crucial. A minimum of 80% attendance is required for these hours to be accredited to your OAA transcript. Please just allow for a few weeks for the processing and reporting of these hours. And lastly, please note that the presenter does not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. Now, I'm very excited to introduce our speaker for today's session, Peter Adams. Welcome, Peter.
Thanks, Shalika. It's a big pleasure to be here, and I certainly appreciate OA having me, and certainly all the attendance today. Thanks very much for attending. So my name is Peter Adams, sorry. I am a senior building science engineer at Stantec. I was part of the Morrison Hershfield group for 25 years, and Stantec acquired Morrison Hershfield about 2 years ago. So I've been doing this for a long time. I spend most of my time diagnosing building problems, some new construction, but primarily investigating buildings, why they are working, and trying to figure out the ones that are working, how to duplicate that in other buildings. I'm a mechanical engineer by training, but please don't hold that against me. Graduated from Memorial University in Newfoundland longer ago than I care to admit. And so, yeah, looking forward to today's presentation. When I was putting this together, I went back to my childhood. This movie here, Bridge Too Far, when I was young, we had two channels. And when this movie came out in 1977, it was played a lot on TV. And so I ended up watching a lot because there was not much else on television. And it's really a movie. I was probably too young to watch it at the time, didn't really understand it, but it's about an operation of the Allies that the Allies put forward in 1944 to take over a number of bridges across the Rhine. And as you can guess, Bridge Too Far, the bridge of Arnhem was the bridge that they could not achieve. And so the interesting thing for me as a kid was, this is a war movie, or a movie where the bad guys, the good guys actually lose. And you're probably asking now, so what's this got to do with thermal bridges and buildings? Well, in this movie and this whole story and this history, the Allies tried to go too much. And I started thinking a lot about, when we're dealing with thermal bridges and buildings, how many bridges can we ignore, or how many can we accept in our designs before we've accepted too many, and then the building is no longer performing nearly as well as we think it would be. So that's where that title comes from, and we'll get into that for sure. First thing, full disclosure, I don't dislike all bridges. I certainly love some of the ones that are more beautiful, like this one. This is one of my favorite structures. So it's not all bridges are bad. So we're starting off on the same foot a little bit here. Let's talk about what is a thermal bridge. The image on the left, I think most of us are probably familiar with this type of thermal bridge. It's a highly conductive material that penetrates through an insulating layer. In this case, it's the shelf angle coming off the slab, penetrating the insulation. The ones on the right a little bit, the one in the middle is not thought about it nearly as much. It's a discontinuity or a misalignment of insulation in a wall. We'll talk more about this later, but you really want all your insulation planes, including the window, to line up in a wall to achieve maximum thermal performance. And the one on the right is almost always ignored. It's the increased heat loss due to an exterior surface area being greater than an interior surface area. So if you think about it, it makes sense. Heat flow is an area function. It's an area phenomenon. So if you've got a larger surface area outside, you're going to conduct more heat to the wall. So that's what a thermal bridge is. Just a reminder, heat is lazy. Just like, your lazy teenager, if you put the fridge in a straight line to them or the treat cupboard, they're going to get there pretty quick and they'll eat you out of house and home. If you put the fridge in the basement and make it harder to get to, then, maybe they'll take their time getting there to get the next bag of chips or whatever they're going for. So heat will follow the path of least resistance. When we're talking about U factors or effective R values for walls, it includes thermal bridges, just for our discussion today. So these bridges, as you can see there, we've got studs and other elements. They degrade the thermal performance of the overall system. They can lead to condensation, thermal discomfort, and certainly increase energy loss, which certainly has been a focus for the last number of years. So where do we find these? Well, common ones are certainly that slab edge detail that I showed you, where you've got a shelf angle protruding through around windows. But basically, it's any type of repetitive structural member, a stud or a joist or a lintel, that it repeats itself across the building envelope. Or it could be a one-off situation too, such as a structural penetration, a column or a balcony. The common one would be a support for a canopy that comes out through an insulated wall assembly to support a roof over an entranceway or something like that. Wall to roof connections or your window to wall connections. Anytime you have a junction of different materials or systems together, you'll often have a thermal bridge. Cladding supports. This is getting better with the introduction of some thermally broken systems out there, which is great. But there's still systems being put up without thermal protection. And of course, edge of walls and floors are common as well. So I stole this slide from this concept of this slide from my friend John Straub. Some of you might know him. Some of you are probably trained by him. The evolution of the building envelope thermal performance, and years and years ago we moved out of caves and started building for ourselves and started off with something like this maybe, and with a mud wall maybe we're getting something like R4, right? And we move forward. This is the Tower of London in London, obviously, built in about 1000, year 1000. And, here with just the thickness of the walls that we have, maybe it's about an R5. This is the Justice Building at Parliament Hill. I had the pleasure of working on this building when I was at the National Research Council. Just because it's a thick stone wall, but it's got terracotta brick on the inside. It's got plaster, just by all the different layers and some air spaces, maybe you achieve an R9 for this building. This condo building, or apartment building, there are hundreds of these in the Toronto area, going up in the 60s and 70s. It started to introduce some insulation into these walls, and maybe we get to R11. What about a semi-modern window wall system or curtain wall system? What do we think the R value for that would be? So should we get poll number 1, please? Okay, so if you thought it was R20, I can certainly understand your optimism. Okay, looks like the majority of you are picking R4, which sadly is about right. I did have an argument. I remember discussing this building when it was being constructed, and having an argument with one of the designers at the time who was adamant that the walls were R20. at the middle of the spandrel panel over the slab edge, it might have been R20, but for the most part, that building was operating as an R4. And a little bit surprising. Now this little guy looks like he might be doing something else at this time, but he's surprised. And either way, it's a pretty crappy situation for our wall systems when we've got modern buildings going up like this. But there is hope. So this picture is one of my favorites, being a building science nerd that I am. I call this the poor consultant's thermography picture, where you can see a lot what's going on without even using a thermographic camera. If I zoom in a little bit, you can see here there's some areas where there's condensation, right? These areas here, and then there's some areas where there's no condensation. So we've got pole number 2, please. There'll be a test later. No, just kidding. Okay, we're about split. So I see the poll results coming a little bit delayed. That's okay. We're about split on this. So 24% said there's no way to tell. 44% said the without condensation is spandrels, and 33% said the areas without condensation are vision areas. Well, I can tell you the areas without condensation are vision areas. And the reason for that is there's a little bit more heat conducted through the glass, which keeps that glass on the outside just warm enough that condensation is not going to occur. The other areas where you've got an insulated spandrel assembly, it reduces the amount of heat flow through through the assembly, and that surface temperature gets a little bit cooler. And this building this picture was taken at a real sweet spot where the dew point temperature was just about, the aerosat set close to saturation. We're just dealing with kind of on the cusp where the glass is just about to condense and not condense. And just that little bit of extra heat coming through the glass is enough to prevent that from happening. What struck me most about this picture is that, apologies, that there's a lot of areas where there's still no condensation in the spandrel sections. And so that means there's heat transfer there. There's maybe not as much heat transfer as the glazing, but there is certainly more heat transfer here than you would expect from an insulated spandrel assembly. You can even see the heat transfer as a result of the stick pins that are holding insulation into the back pan. There's little areas here. There's just enough heat coming through those pins to warm up the exterior glass in those areas to prevent condensation. But what struck me is that, and what I mean by poor consultants infrared here is that if you're a building mechanical engineer and you're designing your system based on the thermal performance of this wall, and you're assuming this whole panel here is going to give you the thermal protection that's expected on paper, well, you're gonna grossly underestimate the amount of heat loss that you're going to get for this building. And that's why for many, many years, it's getting better now, but for many years, a lot of the predictive equations for thermal performance for a building were always more, the results were always better than what the reality ended up showing as the building started to operate for a number of years. So this was a big deal. If you're designing this, you're going to assume that all this is at, say, R15 or whatever, but really it's not. And if you take this over the whole area of the building, that adds up to quite a bit. And we're going to get into more of that as we move forward. So this is what's happening here. You've got quite a bit of heat coming through the glass. You've got a lot more heat coming through the framing, the metal parts, and then less heat coming through the insulation. So it's not just academic. We've got a lot of buildings that look like this in the Toronto area and in Ontario and across Canada for that matter. and for a while it was kind of, well, yeah, you're going to lose more heat, and then it's going to be your energy bill is going to be higher. But we're starting to see some real world implications of these decisions to use some of these systems that don't provide the best thermal performance. This was a brand new condominium corporation we were doing a performance audit of. And one of the things we noticed when we went into the suite over here, you can see, this is a brand new building. There's already condensation occurring on the inside of the glass. There's a little bit of snow and ice that accumulated outside, and now you've got condensation on the inside. But more telling to me is that, this chair is now pushed away from the exterior wall. In the old days, you had an opaque wall here, maybe with a punch window. You could put your furniture right up against the wall. You could sit and watch your Netflix or whatever. Now, if you're too close to the wall, you're too cold. You've got this cold surface that's kind of sucking the heat from the back of your head as you sit and watch television or read or whatever you're doing. So everybody's moving their furniture away from these walls, and your 800 square foot condo is now a 700 or 600 square foot condo because this part of the wall, the floor here is not really usable for furniture or for living. So it's not just academic anymore. There's real world implications of some of these decisions. But it's not all doom and gloom. My 10-year-old self was heartbroken when Han Solo got trapped in kryptonite, but there is hope on the horizon. So when do we start caring? Well, the ancient way, all our really large stone and masonry buildings from 100 years ago or whatnot, that was kind of the ancient way where we had boilers and we had tons of heat flowing through the wall. We still had a thermal bridge, but we really didn't care because the amount of heat coming through the wall was so great anyway. The little bit of extra heat that was coming out through the thermal bridge really didn't matter that much. Kind of the old way where maybe we should have cared more, but we didn't. The same thermal bridge, but we added some more insulation. Now there's less heat coming through, but it's still quite a bit more than what was coming through in the thermal bridge. But the new way, though, we're adding a lot more insulation to walls, and so our building is becoming a lot more efficient. And you can see here that even though the amount of energy, the thermal bridging has not changed, the amount of energy that's coming through our clear wall areas is greatly reduced. And so now this all of a sudden becomes a very large percentage of this whole energy loss for the building. And so we can no longer ignore these thermal bridges. They have to be included in our energy calculations and our designs. Otherwise, we're just kidding ourselves. So back about 15 years ago, maybe 16 years ago now, ASHRAE was starting to care about this stuff too. And the research project 1365 was put out. And Morrison Herschel at the time was a successful contractor for that work. And so these are slides captured from a presentation given around that time. And at that time, the intent was to pick 40 common North American details and then do three-dimensional heat transfer analysis on those and try to figure out what is the effect of the thermal bridging. So these assemblies included things like exterior insulated steel studs, concrete mass walls, curtain walls, precast panels, brick veneer walls, all assemblies that are quite common. We didn't want to pick anything that was a little unusual yet, figuring that might come should this catch wind and move forward. But that was kind of the focus back in about 15, 16 years ago when this project first started. One of the things we had to think about and try to come up with a way to report this information once we started getting all this three-dimensional work done is how to a certain nomenclature. How do we report this? So we end up with three different types of heat transfer. We basically had the clear wall area, which is our U naught. Now you can see here that this clear wall area includes all the thermal bridging, such as the girts and everything else, but that's kind of our baseline wall assembly. And then we have our psi values, or our heat loss per length, so our linear heat transfer, our linear thermal bridges. And then we have our point load heat transfer, or our point thermal bridges, our chi values. And so the idea is that you add all these different types of heat losses together, and you can get a really good, accurate picture of the energy loss in your building and what's really going on. And the concept became quite took a while, and we actually picked up this concept from Europe, this whole idea of linear heat transfer and point load heat transfer. The basic principle is pretty straightforward. You model the whole 3D assembly, such as this here, which would be your clear wall area, plus in this case the through slab area, and you get a total heat loss. And then you model the wall without the thermal bridging element. So you model just the clear wall area. And if you take the difference between the two, you get that additional heat loss from the thermal bridge. So conceptually, or a schematic on the side here, you see the blue arrows, that's basically your baseline heat transfer. And then the additional heat transfer or heat loss to the slab is what you tack onto it. So you always have what's in the rectangle box here. And then every time you have a linear heat transfer element or a point load heat transfer element, that would be an additional to that baseline load. So if you look at it from a mathematical standpoint, your Q naught is basically your heat loss through the total wall of the building. Now as I mentioned, you're assuming all the thermal bridging that occurs is going to be included in that baseline wall assembly. And then you take the sum of all your linear heat transfer elements times their total length. So if you've got 300 feet of something, you add that up. And then you take your total number of point load elements and you add those up. And this whole assembly here becomes, or this whole equation then becomes your total heat loss for the building. So it's the clear wall area down here times the total area of your building, wall area of your building, plus all your linear heat transfer elements all added together, plus all your point load heat transfer elements all added together. So it ended up being a fairly simple math. Once the hard part was all the 3D work that's been done. And the intent of this 1365 research project was to take the modeling away from the hands of the users, get the modeling done first, and then make it a lot easier for people to use the information that came out of it. Now, it was tricky. With 40 details, it was unlikely you're going to find a detail that matched what you had in mind for your building. You might get close and you'd have to maybe extrapolate between two different assemblies, but it was unlikely you're going to find something exactly what you wanted. Now we've got over 800 details that have been produced, and the chances are pretty good you're going to find something that's pretty close to what you've got in mind for your building. So it's much more user-friendly now, or much more applicable that you've got all these details at your fingertips. The information that came out of that research study was put together into a thermal bridging guide. Some of you might be familiar with it. We'll get more in detail this in a minute, but basically the thermal bridging guide had an appendix with Appendix A and B. Appendix A was kind of what the wall looked like with all the assumptions about the materials and how the wall was put together. And then Appendix B was the thermal performance information that came out of it. We'll step through that in more detail in a little bit. Another reaffirmation that not all bridges are bad. Another one of my favorites, of course, the Tower Bridge in London. So, we started publishing information from this, and we weren't very popular for a while. Sometimes reality is a difficult thing to swallow. And so a lot of the window wall and curtain wall manufacturers weren't that pleased that all of a sudden we're showing their systems are performing a lot less than what everybody originally thought. People probably knew that they weren't as good as some of the numbers that were being put forward in the literature, but I think the level of loss of performance was more significant than anybody would even imagine. This is a very telling graph here. The blue line is a detail with air in a stud cavity. It's just an exterior wall. The dark line, or the purple line, is the same wall with foam in the stud cavity. Now, the interesting thing is if you put, so on the left-hand side is your R value for spandrel section, and on the bottom axis is the backpan insulation, so the book value of the insulation you're putting in the spandrel. And you can see if you put R5 in the backpan, for the wall that has the spray foam, you have a level of 8.2, an R value of 8.2. For without the spray foam, you have an R value of 4.2. When you put an R value of 15, which is pretty typical for a lot of spandrels, your actual R value without the spray foam is less than 5. If you decide to put spray foam in the cavity, you can get it up to 8.8. And of course, adding R25 in the spandrel, you're only going from 4.8 to 5 on the unfoamed wall, going from 8.8 to 9.1 on the phone wall. And you can see there's certainly a diminishing return here, but it's astounding to me. And we first kind of saw this where we had to double check it, triple and quadruple check it, that this is actually the case where a back pan with R15 insulation, it actually only provides an R value of R5. And this is really because of all the metal that surrounds our back pans. You've got insulation in the middle, but then you've got aluminum that wraps around and connects back to the exterior of the building. And so you lose a lot of your thermal performance from that connection. And, you can see, when the building on top left was a building that I saw from the Chicago boat tour, the architectural tour from the Chicago River, which I highly recommend. It was fantastic. But you can see these types of details everywhere in our construction. The one here, this is the Absolute Towers in Mississauga when they're under construction. It's a little bit of a cheap shot. I mean, this is an air-cooled engine. And the thought, of course, here is, should we actually design our buildings to look like things that are designed to exchange heat with the outside air? Now, concrete's not nearly as thermally conductive as aluminum or steel, but I think you get my point that, why would we design buildings that look like they're trying to lose or gain heat in the summertime? Food for thought. There's some debate out there for a while too. Is a balcony worse than an eyebrow? Is it worse than exposed slab edge? And when you look at the numbers, really, all these three type of assemblies are basically all the same, and they're all poor, right? The balcony is really not much worse than the eyebrow or the just exposed slab edge. Either way, they should be avoided, right? So as an example, we have a 40-story high-rise building here, a multi-unit residential building. It's a 40% window wall ratio with 5x3 punch windows, sliding doors at the balconies. It's a concrete structure, which is pretty common. Steel stud infill walls. It's clad with metal, thermally broken system, 2 inches of exterior insulation with R20 bat. So the wall has actually got a nominal R value of almost 30, 29.7. And each floor has the same layout and footprint. So if you look at this building, the hard and cold truth of this, we have the R value on the axis on the left. For the nominal wall, as I said, if you assume there's no thermal bridging at all, and you're taking full advantage of the insulation, and you're kind of in the fantasy world of that, your R value is about 30, 29.7. So I talked about the clear wall area, including some of the thermal bridges of the clips and attachments. So if you include that in your model, then you've got an R value of 17.7. Which still not bad, a lot worse than 30, but still not too bad. But then when you take the clear wall and you start considering the slab edges and the balconies and the heat loss you get at those assemblies, you're down to about 11.6. And then if you actually go to full reality, where you're looking at the clear wall, the slab, balconies, and window transitions, you're actually down to about R5.3. So, maybe what you were considering your R17.7 or R18 building is really performing at R5.3 when you start looking at all the thermal bridging through all the details of the transitions and the window surrounds and slab edges and everything else. And what does that mean? So if you look at energy loss or energy use per day, maybe you weren't considering the 13 because that's a bit unrealistic, but maybe you thought it was going to be 21. You're actually at 70 kilowatt hours a day. So that's why, as I mentioned earlier, a lot of the building simulations were underestimating the amount of energy loss that was going to occur when the building was actually functioning because of all the thermal bridges were being ignored, basically. I think he deserves to come back for that, I think. So how do we fix this? What do we do to mitigate these things? Well, the type of strategy depends on the thermal bridge that you're dealing with. A big one, it's codified now, is continuous insulation. That gets us a long way into reducing thermal bridges through our envelopes. Aligning insulation is huge. I worked on a building in Labrador. It was a hospital, and they had triple glaze units, glazing units, and they basically mounted them outdoors. There's a 3-inch disconnect between the wall insulation and the insulating plane of the glazing unit. So they took all these very expensive windows and mounted them outdoors, basically. So there's no way they could perform properly, right? So align your insulation planes, and that includes your thermal breaks and all your windows and doors and all your flashing elements. You want to minimize those conductive elements, right? If you've got a through-wall flashing, is there a way to use a thermally broken flashing? Or is there a way to use a membrane flashing that doesn't have a high thermal transmission, right? So look at how you're flashing and detailing your buildings to try and minimize how many times things go past the insulation. And if things have to go past the insulation, then they're non-thermally conductive. Use intermittent structural supports. I remember I talked about how heat is lazy. If you make it harder for the heat to leave, then you'll have less heat leaving, right? So look at ways you can take away your continuously mounted support structure. Is there ways to reduce the number of connection points back to the uninsulated portion of the building, or the part of the building that's behind the insulation? And then, of course, utilize thermal breaks. You want to use thermal breaks wherever you can in your cladding attachments. We've been using thermal breaks in Canada in our window systems for a long time, but look for opportunities to use thermal breaks either in the products that you're using or in some of the systems that you're picking. We can talk more about that in a minute. So this was a research project we worked with Tridel quite a long time ago. They were interested in thermal break technology at their balcony slabs. People still wanted balconies, so they're trying to figure out a way to reduce. Really, they were trying to reduce the number of complaints due to condensation and cold, but at the same time, they understood that it made sense to make their buildings more efficient as well. So that first image, this is outside here on the left. This is the outside floor slab. This is the sliding door of the window wall system that's sitting directly on the floor slab. There's a spandrel section over here. So that's what we're looking at here. It's kind of looking at it in a oblique. This is the same area, but you'll notice that here, there's an intermittent thermal break here. And so what they did here, they did a custom solution where they would space the structural supported concrete with foam blocks. So here, where there's more heat transfer, there's concrete and rebar penetrating underneath the window wall system, and here there's a foam block. And so this pattern would go in and out, undulate in and out along the wall, where they had areas where higher heat transfer and areas of low heat transfer. And then the last one here, they used an off-the-shelf product called Isocorb, which is from a company called Schock in Germany. And it's basically a thermally insulated slab edge protection. So you insert this between the interior slab and the exterior slab. The stainless steel tiebacks or connectors, rebar, conduct a lot less heat energy than your traditional iron bar. And this is basically a foam core. And so that you can see here, there's actually substantial reduction in the amount of heat that was coming through underneath the window wall system. So it certainly makes a difference. If you start using some of these technologies, you can make a large difference. And you can imagine right away that a person standing on their bare feet on the right side of this wall looking out the window, in this situation, you can imagine that their tootsies are going to be pretty cold, much warmer in this condition over here. So uninsulated balcony, you've got a very high linear heat transfer value, greater than 1. You start using the Isocorb or other thermally broken technologies, you can get down between 0.39 and 0.74. And this, I haven't seen this in practice yet, but certainly on paper, it brings your thermal performance way up. You have a balcony that's supported by an exterior structure that's just attached back to the building where it has to be. So it's intermittently attached rather than having a continuous path for heat transfer. Again, right, heat's lazy, you make it work to get out, you're going to have a more thermal efficient envelope system. So you want to try to avoid this. I think we've talked about this a lot already. You want to avoid the situation you've got exterior cold connected very well to the interior space. You want to avoid this situation. You want continuous insulation at the slab edge, whether it's either a precast panel or you've got some kind of other exterior insulation system where you're covering that slab edge to greatly improve your thermal performance. So you want to try to avoid this situation over here. Going back to the continuity or the keeping insulation in plane in a wall, and then the difference it can make. On the left here, this was kind of the situation I was dealing with in that hospital in Labrador, where you had the wall insulation, but you had the window sitting outboard of the wall insulation. So there's a huge discontinuity between the wall and the insulating value of the window. If you do a better job of lining those up, and you can see the isotherms here, you get about 30% improvement just by moving that window assembly slightly in so that it's connected to the wall insulation. And if you bring it fully in line with the wall insulation so that you've got these vertical isotherms, then you can improve by about 62%. So it can make a really big difference. So this was a condo that we worked on a number of years ago, and we've got our next poll. Okay, so what do we think here? Do we have condensation at the head of the window? Do we have condensation at the stool? Or do you have condensation everywhere? What were the owners of this condominium complaining about? Well, I don't see the results yet, but the owners complain about condensation. Oh, okay, now I have the results. Sorry. 12% condensation at the window head. 58% said condensation at the window stool. That's very good. Condensation everywhere, 30%. So most of you got this one correct. There's an obvious thermal bridge here, right? You've got your wall insulation here. You've got a stool, a wooden stool sitting on top of the, I'm just going to back up a second here. You got a wood stool sitting on top of this curb. This window is sitting outside, just like I was talking about with our Labrador condition, right? All your wall insulation's here. This is exposed completely outside with no thermal value. So this curb is going to be almost outdoor temperature. And so you're sitting your window on top of this curb. This whole assembly down here is going to be very cold, right? The same condition doesn't exist at the top, but down here, not a good scenario. So lots of heat transfer flowing through there. In this case, it didn't have a lot of real estate to work with here. So we ended up using aerogel, which is has a high thermal value per inch, and put that on the outside of the curb, tied it as best we could into the window frame, and that actually increased the performance enough to reduce the condensation significantly in that assembly. So it's much better to do it during the original design than it is to come back and try and do a retrofit. In this case, the retrofit was actually reasonable, but there's certainly additional cost, and it cost more after the fact than it would have been if it was part of the original design. Right. So once that insulation is added, the amount of heat loss through this assembly here greatly reduced. So once you start thinking and learning a lot about how these systems operate in real time and real performance, you can start making improvements on different products that are available. And we've done a lot of work with manufacturers to try and help them improve their systems, their assemblies, or even just individual particular products. So this is an example that came out quite a few years ago now of two manufacturers of a curtain wall system. This is at the stack joint, so you can see anybody's familiar with curtain wall, your chicken head. There's a closure gasket here. One manufacturer of this curtain wall used a plastic clip here to hold this gasket in place, and another manufacturer used a metal clip. And you can see just by looking at the plastic clip, it's bypassing the space or the window. Right? It's bypassing the engineering that's gone in to try to make this a better thermal performing pane. If you use a metal clip, you're bypassing that. If you use a plastic clip or a non-conductive clip, you're not. But the results just from making that change from a metal clip to a plastic clip are pretty dramatic. So this was a 2D thermal analysis done. On the left here is with the metal clip, and the coldest interior surface temperature for that part of the simulation was 1.6 degrees Celsius. When the manufacturer started switching to a plastic clip. We did model the results. That 1.6 degree temperature went up to 9.1 degrees. So that's a significant difference in temperature just by making that one small change. And if you're a mechanical designer, with this type of assembly, condensation in condominiums in particular is always on the forefront of people's minds and trying to reduce it. In this situation here at 22 degrees C, you can only maintain about an RH of 25% before condensation can be expected, which is not very high. That's a challenge for comfort and a challenge for designers. But if you by just switching to that plastic clip, you're reducing this interior surface temperature substantially, and now you can actually raise the RH up to 45% without condensation being expected. So it gives a tremendous amount of flexibility, increase in flexibility for the mechanical designers to go just from that one small design change. So that's the kind of information becomes available when you start looking at the systems and how they actually operate in real world conditions. There's ways you can improve all kinds of different assemblies. If you look at this deflection header here, down at the bottom here, you've got your spandrel section and your glazing section below. In both cases here where the vision area doesn't change because we haven't modified that, but the opaque areas have gone, if you look at just by moving the thermal break from this location into outboard of the wall to make it in line with the rest of the insulation or the insulating parts of the assembly, you go from an R4.8 to R7.2. So again, making a fairly small change in your design can actually make a overall large improvement in the thermal performance. Working with a metal panel manufacturer, they found, as we started doing the simulation work, we found that 40% of the heat flow through the whole assembly was due to the window transitions. And so without a lot of difficulty, we were able to advise them and tell them, maybe if you made this change and this change, there are some real improvements to be had in that system. And so without making a lot of change to the manufacturing process, they're able to come up with a much better product detail and overall better performance. And I mentioned these before, there's lots of ways to stand off your structural support now for your cladding from the wall system without, to reduce the amount of heat transfer that's happening. Lots of these clip systems, and you can see they end up incorporating some kind of insulating piece against the wall. And so you're really, the idea is, of course, to reduce that amount of heat transfer into those metal assemblies. So what are the benefits? Well, I think we've probably touched on a lot of these already. There's certainly improved thermal performance. That's a big one. Reduced condensation risk. It's interesting now we're starting to see condensation performance criteria in RFPs. I've looked at a number of projects now where they're actually, one of the line items is that you can't have condensation under certain operating conditions. So in order to be able to respond to that and meet that requirement, you really got to understand how that building assembly around there is going to operate if you're going to meet that. It gives you more design flexibility too. If you start looking at ways to reduce your thermal bridging, you start being able to have greater vision area. A lot of the buildings we've seen have huge glazing areas. Now, a lot of it was built and constructed at a time where we didn't really understand necessarily how bad it might be in terms of thermal performance. Now you can use real values and real data for performance and actually confidently spec greater vision area. You can start reducing your wall insulation too. If you've got better performance overall, maybe you can reduce that wall thickness and of course open up more usable space at the interior. And the less materials you use, the lower carbon footprint you have. And so there's lots of trickle-down benefits of really understanding and designing and picking better thermal performing assemblies. So back in 2017, the future of energy standards, this was a slide I put forward. And we talked, talked about different approaches to account for thermal bridging. I say here we're currently working hard to have thermal bridging better represented in codes and standards. That's back in 2017, and so I'm happy to say that that's come true. A lot of the codes and standards now that are being used have certain elements of thermal bridging adapted to them. I'm not going to go into these details. I'm going to touch on them very briefly, but the National Energy Code for Buildings, the 2020 version, has substantially increased the thermal bridging requirements, as has ASHRAE 90.1 2022. IECC is not used in Canada very regularly. It's mostly used in the United States and other jurisdictions. But that also, the 2024 version also has increased thermal bridging elements. Now, these standards are not referenced in the Ontario Building Code yet, but I say yet because eventually they will. And the current code does have requirements for 90.1, and you can either use 90.1 or any NECB. And the versions that are quoted do still have some thermal bridging requirements in them, but not nearly to the level as these new standards do. So the 2020 version of NECB basically says all climate zones in Canada must consider thermal bridges for thermally closely spaced repetitive structural elements, major structural elements that come through or intersect with the envelope, and of course all their glazing, spandrel, parapets, all those transitions, corners, edge of walls, the secondary structural members have to be considered in the 2020 version. The 2022 version of 90.1 is applicable for climate zones over 4, so certainly that would be all parts of Ontario. If you have a material that has a K value of less than excuse me, less than 0.433, it can be ignored. And really what the overall overarching philosophy behind the new version of the standard is, you need to consider wall to roof connections, intermediate floors, balconies, exterior cladding supports, window wall connection. That's really what it comes down to. The current version, or the version that's referenced in the OBC, there is some allowances for thermal bridging through particularly metal wall systems, but it doesn't nearly go far enough. So this actually brings it a lot closer. You can do a trade-off or a performance path as well. And then there's, that uses, I guess, default values, and you can trade off to achieve compliance that way. It's a pretty complex system in general, but it does work, and we're quite pleased that we're finally seeing the thermal bridging effects encapsulated in our codes. The IECC, as I said, it's not used in Canada, but it's similar to 90.1, a little less complex, and they add some other structures to that. So you're going to say, so where do I get all this information, Peter? Where can I find what I need to find to help me with my building design? Well, the ISO 14683 International Standards Organization, I mean, they have a catalog of values. They're pretty conservative, but that's a pretty easy kind of quick check you can use. Manufacturers for most of these systems now are they have their performance values put forward, and largely thanks to the work that was done through that ASHRAE research project, now the values are a lot more accurate than what they used to be, because people expect it to include elements of thermal bridging that where it wasn't included before. And then the thermal bridging guide, really, I'm hoping some of you have already used this or are aware of it. It's a kind of the result of that 1365 report that BC Hydro adopted and produced this thermal bridging guide. And I'll get into that in more detail. So the old version of the guide, and we'll get into the new version now. The new version's online, and I'll give you a small demonstration in a little bit. But the old version of the guide includes Appendix A and Appendix B. I've already mentioned that. The Appendix A is kind of the assembly on the left-hand side. You'll see all the materials listed here, all the assumptions that were used for its conductivity, density, specific heat, all that important stuff to reproduce the simulation if you wanted to. And of course, the geometry. In this case, we've got an insulate. Excuse me. We have an insulated wall assembly, exterior sheathing, insulation. The Appendix B is all the good stuff, all the stuff that comes out of the simulation work that shows the performance for that wall system. The first thing you notice that the titles are pretty long, and they have to be because there's slight differences between a lot of these details. This particular one, exterior and interior insulated 3 5/8 by 1 5/8 steel stud, 16-inch on center, wall assembly with horizontal Z girts, 24 inches on center, supporting metal cladding, clear wall. There might be different spacing. There might be another assembly that's different spacing. So there's a lot of similarities. So you have to be very careful of what you're picking, excuse me, so that it actually matches the detail that you're interested in. The thermal performance indicators here, it shows you, so this particular assembly, the baseline condition is R 14.2 within the stud cavity. So it's a 3 and 5/8 stud. So it's full with insulation that gives you R 14.2. So that's kind of your baseline insulation. So it gives you some information like that. This is your 1D performance versus the assembly performance indicator. So it makes sense here. This is your 14.2 in your cavity plus the exterior insulation. So in this case, the exterior insulation is 0. So, big surprise, the book value for your wall is 14.2 or 14.2. But when you do your thermal calculations with the 3 simulation, you end up with an R of 9.2. So it's quite reduced. You think you're getting 4.2, but you're actually getting 9.2. And then you can see the values for all the exterior insulation that's added, R5, R10, 15, 20, 25. This is all insulation that's added outboard of the wall assembly in the form of that foam insulation, that continuous foam insulation. And you can see these are your book values. It's basically, R 14.2 plus 5 is 19.2, but the actual performance value is 13.4. And of course, your inverse is to give you your overall heat conductance. So that's that. It's also graphed. So that information is put on the graph to give you an idea of where your performance actually lies. So here's your assembly effective R value, and here's your one-dimensional or your nominal heat value. So for R15, you're actually getting R9, as we saw in the table. And the interesting thing, of course, is you see this thing tailing off. As you add more and more insulation outboard, you actually get a significant reduction in return on investment. Eventually, this thing would flatten out completely. You could add, a million kilometers of insulation outboard the wall, and it wouldn't make any difference. But either way, you're significantly below this diagonal line, which will be the 1-to-1 correlation, right? You add R10, you expect to get R10. You're adding R15, you're getting R9. The information that came out of this report of this study also includes some surface temperature information. So for every assembly, there's typically 1 or 2 or 3 or 4 points where it'll actually calculate the temperature index. It'll show you these are sensitive points within the assembly that you can use to try and, you can figure out condensation potential or things like that. So the graph here will show you where those temperatures are, and then the table down here will actually give you those temperature indices. And you can kind of think of temperature indices as a percent of interior temperature. And so the lower the value, the worse the performance is, basically. Right? So to give you all these for 0 exterior insulation, you get R5, R10, R15, etc. outside, and gives you the changing temperature indices for both of those points. So you can use that to, as I said, to figure out your condensation potential. And every assembly will look a little bit different. So that was a clear field, clear wall example. There's hundreds of examples too of linear heat transfer elements. This is a slab edge. This is grade. There's a concrete slab and footing, foundation. There's the two different assemblies here are with an aerogel at the slab edge and without. So, and you can see what the isotherms look like over here. And then you'll have a table for the linear transmittance that will be included for each of these linear transmittant elements that'll give you that value for each of those scenarios. In this case, the scenarios are conventional without aerogel and with. There's a substantial difference in the heat transfer here. So it helps. The aerogel certainly helps. So the thermal rigidity guide, it was great and was used extensively in industry, and it offered a lot of information for people. And the nice thing about it that you didn't have to do a lot of the 3D simulation work yourself. It was already done for you. And so for that reason, it was widely used, I think. If you could add and subtract, mostly add, I guess, even if you could just add, you could figure out a really good picture thermally of how your building is expected to perform. And the guide allowed people to compare different details and pick one that actually made sense for their work and for their building, and focus on the elements that cause the most grief. Now, it was a little bit cumbersome to go through the Appendix A and Appendix B. So the whole catalog of details has now been put online, and it's freely accessible for everybody. So if you go to thermalenvelope.ca, not right now, because hopefully you're listening to me, but if you go to thermalenvelope.ca, you can get access to basically it's the whole contents of the thermal bridging guide, except it's updated regularly, and it's a lot easier to use. You don't have to flip back and forth between PDFs and cut sheets and whatnot. It allows you to pick and choose and compare different assemblies much easier. So really how it works is there's the database portion, which is all the details. There's the collections portion, which I'll show you in a second, where you can actually build your own buildings within the software. As I said, it's freely accessible. It's supported by BC Hydro, so they don't ask for any user fees or anything like that. So it's quite open for everybody to use. Your welcome screen is basically this, this generic building here, and you can pick whatever you want in terms of what type of cladding system you're interested in. So let's pick clear wall assemblies. So you click on that, and it'll open up all the catalog elements for all the catalog elements for clear wall assemblies. And the focus here is you find that clear wall assembly that matches what you're either intending, or you find a clear wall assembly that gives you the performance that you need. There's some interesting tools here to help you make those decisions. There's lots of keywords. There's all kinds of different backup walls and options you can pick here too. The other thing which is kind of neat is this minimum thermal performance slider. So right away you can start picking systems that have, you won't see things that have a worse performance than whatever your slider shows, for instance, right? So that actually helps narrow things down very quickly. If you go into any of these assemblies, and we'll just pick this top one here, what it will do is it'll open up this page. It'll give you a lot of the basic information about all the output from that simulation that was done for this element. It'll also give you the Appendix A and Appendix B cut sheets from the actual thermal bridging guide. If you click on one of those, it opens up fairly quickly. You'll actually get the full page of the Appendix A, which includes all the information that you would expect to see and what we just went through. Right? So it gives you detail 5.1, gives you all the information that's available to you, so that if you want to go back, you go back to the catalog here. From here you can start picking different details as well. You can pick a glazing transition. Okay, hang on. Delay. So here's your window spandrel, right? So you got all these spandrel details that you can choose from. It also allows you, if you've got two systems that are similar, but your system is slightly in the middle, you can certainly do linear interpolation to figure that out. But with over 800 details now available, you can see here there's 800 details. There's a good chance you're going to find something that's going to be useful for you. Whether you're going to pick from this catalog, or you've already got a system in mind and you can find something that looks very similar. The interesting part too is under collections, you can start building a collection of details to build a building basically. And there's an archetype building here that has already been assembled as an example. And so you can see that this is already including a number of different assemblies. And you can start building this. And through this function here, you can start comparing different assemblies as well. So you can click compare. You can select a number of clear field transmittance, for example, compare them all together. You can pick a number of different elements and compare all together and try to find out which one gets you to your happy place. So it's a very interesting and useful tool. Great for a Friday night with your family if you're up to entertaining them. But there's lots of information here. I encourage you to go in and play with it a little bit. Sign up, get yourself a free account. And there are some help files available. There's some videos that'll help you get through. But it is a really great tool, and it makes it a lot easier to find the assemblies that were normally a little bit of a challenge going through with the appendix in PDF formats. Time to talk about that was a lot of thermal bridging bashing. So again, another beautiful bridge, the Brooklyn Bridge in New York City. There's other tools available as well. There's a spreadsheet online that I mean, anybody can make the spreadsheet. It's basically totaling up all the different, linear transmission area lengths, your total wall areas, your number of heat transfer points, thermal bridging. So you can do your own spreadsheet, but there is a spreadsheet out there that the search changes a little bit. I did test this the other day. So if you search for a building envelope thermal bridging calculation spreadsheet, you will get to it. And you can download that, and it just kind of sets things up for you already to make it easy to start entering the information either from thermalenvelope.ca or from the thermal bridging guide PDFs. So it's basically just a simple spreadsheet. That's all it is. If you can add, you can do this work. So going back to our original MERB, we talked about as an example of how you can use this. It's really, you go through the drawings, you start doing takeoffs from the different areas, right? So here you've got 624 feet of balcony length. You've got 624 feet of balcony door head. You've got 200, almost 2,500 feet of intermittent floor, 7,600 feet of window jamb, right? So you get the idea. So you start going through your drawings, and this particular building is repeated floor to floor, so you can do this fairly quickly, right? You're not dealing with a complex architecture here. So once you do one floor, you can multiply it by the number of floors you have, and you've got a pretty good example, a pretty good total of what you've got. Just have to be careful not to double count things when you're doing those types of calculations. And so when you start looking at where all the heat loss is coming, you can see it'll start breaking this. You can from that spreadsheet and the calculations you do, you'll start seeing where all your biggest problem areas are, right? The interesting thing about here, so let's clear wall area, assumes an R value of about 18, 29% of the heat loss. So before thermal bridging was considered, this was basically would represent your entire heat loss for the building. Like in what I'm going to call the old days, the pre-thermal bridging days, this part of the pie here, this 30%, that's all you got. So when you did your thermal performance calculations, you're only getting 30% of the energy loss. All this stuff here would have been ignored. So again, no wonder that our prediction equations and a lot of our modeling that were done for the whole building was not accurate. We're ignoring way too much. And this is, these are definitely thermal bridges too far. We're ignoring way too much of reality here to get anywhere close to what the real performance numbers are. Give an example too of starting to pick better details. We've talked a little bit about better details. So certainly here you've got, your typical windows where you've got insulations a little bit misaligned. You may have a continuous balcony. If you're using 2-inch wall insulation, you get R 5.3. If you use 4-inch wall insulation, you get R 5.8. But if you go to a mitigated detail where you start aligning your wall insulation with your windows, maybe you use some thermally broken balconies, you can quickly get a pretty substantial increase in performance. If you go to a little more fancy and you go to an enhanced balcony situation, you're not getting nearly as much of a jump in performance by doing that. But if you get yourself to the mitigated details, you can make a big improvement, but really small changes to the envelope design. And what's interesting here too to me is that 2 inches of insulation with a mitigated detail is much better than a wall with 4 inches of insulation with an old style detail, right? So less material, small changes to the detail, you can get a much bigger thermal performance increase than just adding insulation to an old style or an old school detail. So lots of smart choices to be made for sure. So in summary, thermal bridging, I think a lot of these things are obvious. Increased heat loss, condensation risk. It comes in many forms, which we talked about. An overarching concept for me is just don't do silly things. I see a lot of silly things being done, either in the field or in design. Try to avoid silly things. The thermal bridging mitigation. There's lots of strategies that we talked about. The building codes are getting there. They're not, like I said, a lot of the standards that are referenced now they have some thermal bridging requirements in them, but stay tuned. And it's a good idea to get prepared for that now with your designs now. Start thinking about this so that you're ready when the codes actually do require a lot more attention to the thermal bridging. And of course, look at your resources, the thermal bridging guide, and of course, thermalenvelope.ca. This is the bridge here. It's near Lucca, Italy, which is a fascinating bridge to walk over. Sorry, this is a repeat slide from the one before. My apologies. And I like to leave my presentations a lot with kind of anecdotes from the past. So parting words of someone else's wisdom. Application of insulation over the entire exterior of a wall provides an ideal solution for the problems presented by thermal bridges. Many of the thermal bridges occurring in present-day construction can be avoided or their effects minimized if they are recognized in the early stages of the design. It sounds pretty prescient and modern, right? Well, that came from the National Research Council in 1963. One of my colleagues used to say we're in great danger of stealing sorry, I can't remember my anecdote. Um, Once again, sorry, my apologies. Once again, the ancients have stolen all our good ideas, is what he used to say. And so a lot of the stuff that's we've figured out a long time ago, people think it's new and great today when maybe it's not. Maybe it's a concept that's been around for a long time. And thanks very much for your attention. Certainly welcome any questions or comments, shared stories.
Great. Thank you so much, Peter. As he mentioned, we are going to move now on to the question and answer portion of the webinar. I see there's already quite a few questions in the Q&A window, but if you are wanting to ask Peter a question or, again, share an anecdote, feel free to do so in the Q&A window that you'll find at the bottom of your screen. So we will get started with the Q&A here. So our first question is about ASHRAE. So this person has asked, does ASHRAE look at the passive house system closely and borrow from it? Do they have any disagreements with passive house?
Unfortunately, I can't speak for ASHRAE, so I don't really have a good answer for that. I'm not sure.
Okay, no problem. So our next question asks, what is your opinion regarding adding a stud assembly with batt insulation and vapor barrier behind insulated window spandrel back pans? Is there a code compliant spray foam solution?
That's a really loaded question. So there is a bit of a danger there because if you allow interior air to get past that layer, you by adding a layer of insulation and thermal resistance on the room side of that, you're making that window really cold and you're depriving it of any heat or airflow from the inside. So if you do in that situation, you need to make sure that you don't get interior air into that space. The other strategy would be to vent that space if you can. So have that space open to the outside somewhat so that the thermal value of your interior wall provides all the thermal value for that wall, or most of it at least. But if any moisture does get through or interior air gets through and there's some moisture in it, it has a chance to vent out. So there's a lot of what ifs in your question. I'm hoping that gave you some clarity.
Great, thank you. Our next question asks, is there a best practice to consider when detailing where to place a window within your wall? I understand aligning the window with the insulation, but for example, would you align the outside face of the window pane with the outside face of the insulation?
The good rule of thumb is the glass itself, the insulating glass unit is separated by a spacer. And that's really your line of your thermal performance, because if it's a gas-filled IG, for instance, that's what you're relying on to provide the thermal performance for that window. So best practice to have the middle of that align with the middle of your insulation as best as you can. Now, as you saw from some of the examples we talked about, you move the window a little bit either way, you're still going to get pretty good performance as long as you don't move it too far. So having said, you want to try and line up as much as you can the middle of the glass with the middle of your insulation. You recognize you can't do that all the time, so you kind of do the best you can. The idea is that you're aware that it makes a big difference, or can make a big difference, where you line up your window, and you kind of line up as best you can given the constraints of whatever the project you're working on.
Okay. This is another question, I think, related to ASHRAE, but this person has asked if you can elaborate on the new SB10. In brackets, they've put ASHRAE 90.1 and 189.1. Evolution in OBC 2024 and future changes as well. And they said that any advice would be helpful in terms of getting ahead of the game.
Well, the new version of SB10, checked this recently, it still refers to the old versions of NACB 90.1. So the new standards, new versions of the standards are not codified yet in Ontario. But they probably will be down the road. So if you start becoming familiar with those two standards, I think you'll be well prepared for the future. You can still build buildings using those older standards because they're part of OBC, even the new version of OBC. But the amount of thermal bridging that's included in that version of 90.1 is minimal. If you start looking at the calculations, it's better than what if you assume that there's no thermal bridging, but not nearly as good as if you assumed that you're taking into account all the thermal bridging. So I'm not really sure I'm answering your question very well, but it's becoming familiar and aware of what's coming down. Maybe it's the next code cycle where we'll start seeing these new versions of the code new versions of the standards that are incorporated. So you might have some time to start to adjust your thinking a little bit. But I was a little disappointed we didn't include some of the new standards in the latest code revision, but it is coming. So, the win that we're considering is that it's been added to the standards. That was a big fight to actually get 90.1 for 90.1 as an example, to get ASHRAE to include those elements in that standard. I used to attend, I still do sometimes, the ASHRAE meetings, and I had several friends that sat on the 90.1 committee, and they come out of those committee meetings look like they've been hit by a truck. There's a lot of people sitting around the table, and a lot of people have their finger in their pie. And it was quite a monumental lift to even get that level of thermal bridging consideration in the standard in the first place. So baby steps, right? But we're going to get there. So awareness, right? I think you really want to develop an awareness for yourself and start thinking a little bit differently. The old days are gone. A lot of the low-hanging fruit that we used to rely on in terms of HVAC systems to give us our performance level increases, those are all gone. Those are all normal now. So we have to look for other ways to get better thermal performance, and thermal bridging is a big one right now. It's kind of the new thing that we have to consider to get where we need to go.
Okay, thank you. We have a question here asking if you can speak to what level of combustible material, i.e. plastics often used in thermal clips, is acceptable in non-combustible construction. What is typically ring accepted by AHJD?
Yeah. And this is kind of an age-old question, right? Can you put spray foam in a non-combustible building? And the answer I've always been given by our code people is you can put a little bit. And so how much that is, I think, depends on the situation that you're dealing with, depends on the material. You can put some combustible materials in a non-combustible building, but it's usually a fairly small percentage. And so you might have to look at other alternatives in terms of your product selection. So if you're thinking spray foam, maybe you can't do spray foam. Maybe you have to use a mineral product or something that's non-combustible. But there's ways to detail all these things without having to use any plastic. There's it might affect your design choices, but there is some flexibility there to use these types of products on a non-combustible building.
Okay. Someone's asked, what is your viewpoint on fully outboard insulation for high-rise MURBs? And what are the key risks or detailing challenges to watch out for?
Hmm. Yeah, the big one is if you're putting all your insulation outboard the wall and you're putting these cladding systems out there, you've got quite a cantilevered load, right? You think about all the insulation you need to give your full wall performance requirements. That cladding, whatever it is sitting pretty far out on the wall, and so all of a sudden, it's kind of a catch-22. You've got all these structural elements passing through the insulation back to the structure in order to hold your cladding. Um, so it can, there's a challenge in that situation too. You're often dealing with a challenge with wall positioning too. Window positioning. Where do you put your windows and how do you mount everything? But it can be done. I think most times certainly when you put all your insulation outboard your wall, your condensation risk goes way down because any cavity you have on the inside, everything stays room temperature basically. So there's a lot of building science benefits from doing that. But then you get these practical concerns. So it can be done, but you do have to look at those hanging a heavy cladding on outboard of 6-inch clips, for instance, is a difficult thing to do, but it can be done.
Okay, great. Someone has asked, are there concerns regarding the long-term durability of plastic or other non-metallic flashings and fasteners compared to metal?
Yeah, I would say there are concerns. I think you have to rely on the material for that particular fastener and the longevity. Uh, for me, it's I've been around a long time, and so there's certain fasteners that have been around a long time I tend to trust, right? A lot of these plastics, if they're not exposed to UV, can last a really, really long time. And so you have to be careful that you're not putting them behind like an open joint cladding system, for instance. Um, so given the choice, I would probably pick what I'm used to and what I'm comfortable picking. That's often going to be a metal clip or fastener. If I'm looking for a thermal advantage, then I'll look elsewhere. But I'll be very cautious to pick things that have either been around for a while or I've got some comfort that they're made of a material that I know is UV stable um, and is expected to give good longevity. I mean, we've been using plastics in buildings for a very, very long time. And a lot of times it works quite well. So
Okay. Someone has asked, are the details using combustible insulation at window backpan systems permitted by OBC 2024?
yeah, that's a bit too generic. I can't really comment on that, Rana. Sorry. I'm
Okay,
not
no
sure.
problem.
Yeah.
Someone has asked, how bad is a continuous metal upstand for a parapet?
Continue to upstand for a parapet. I think if you're thinking if what I'm picturing in my mind is what you're thinking is the window wall or curtain wall extending past the roof line. If that's the case, then it can be problematic. It's best to separate that wall system at the roof line. For instance, you have your wall system that comes up and terminates at the roof, and then whatever you want your parapet to be, you put outboard of the roof insulation. So it's basically just a upstand that's not connected back to the building. And we see problems a lot of times where these flyby details where the curtain wall will bypass the roof slab and then you get interior air into those spaces and which can lead to condensation and other problems. It just makes it easier to have a continuous thermal envelope if your wall system stops at your roof line and you wrap that corner in insulation, and then you can put whatever the heck you want on top of that. So separating out those assemblies, it certainly would serve you well. And like I said, thermal performance, if it's sitting outboard the insulation, it doesn't matter anymore.
Okay. Someone has asked, is it a good idea to place a baseboard heater near the balcony door to help minimize the impact of thermal bridging? And what factors should I consider to ensure it works effectively?
Yeah, putting the baseboard heater there is not really going to fix your thermal bridging. The bridge is going to be there. You're going to be trying to mask the problem, right? You're going to have a cold floor and a cold door if it's sitting on top of the floor slab. So the electric heater is really using you're using fuel basically to compensate for what might be a poor detail at the slab edge, right? So I would try to get away from an active situation like that or an active solution, such as applying heat if you can, and detailing things a little bit differently so you can avoid the thermal bridge in the first place. Um, but if you do that, the heat certainly will help avoid condensation because it'll be radiating heat onto parts of the window wall or curtain wall or a wall, whatever it is, and will increase the surface temperature, and that will help avoid condensation.
Okay. We have just a few questions left, but if you are working on or typing or thinking of a question, please do put that in the Q&A box. Um, but here we have a question. So they've asked, what materials do you recommend for thermal clips? Is there a thermal clip that is non-combustible?
I mean, I can't really recommend or endorse any. I'm just happy, to be honest, to see them. Almost every architectural drawing set I see now incorporates them. You really have to look at what's best suitable for your project. Um, there's a lot of them out there. In terms of combustibility, that's a question. I don't have an answer to that off the top of my head, but all the manufacturers have their combustibility data and testing results included. So you should be able to go through and gain a level of confidence from that.
Hmm, okay. And last question here. What would be some examples of non-conductive alternatives to common elements that go past insulation line, like flashing?
Yeah, so what I've seen lately is thermally broken flashing, for instance. So you have, instead of having a single piece of metal that comes from the inside through the insulation and outside, you can get thermally broken elements now, and they're fairly common. Now, they used to be a very oddball thing. You get strange looks from the contractor, but now they're not that uncommon anymore. If you can use membrane flashing, if it's supported adequately with the structure alone, you can use a membrane flashing, and they have a very low conductivity value. Sometimes it's just the way you lap certain things, or if you're using a girt at the base of a drain wall system, how you position that girt. Um, you can sometimes add insulation outboard too, and cover with a flashing in order to keep things warm. So there's lots of ways that you can manage that detail, and lots of different products out there. But there are some new products that are helpful, like those thermally broken flashings.
Okay, great. Thank you. So that's all the questions I see. I don't think any more have come in just yet. Um, but we're almost at our time anyway. So I think I will move on to just a few closing announcements that I have for all of our attendees. But before I do that, of course, I want to thank Peter for an excellent presentation. Especially love the memes. So that was fun to see those interspersed throughout. And we've got a lot of great questions as well. So thank you to all of our attendees as well for your participation and for your great questions. Again, a few closing announcements. Excuse me. So, for those who are seeking continuing education hours, again, the OAA will record your participation in this webinar on your OAA transcript, so there is no need for individual reporting on your part. We just kindly ask for your patience at this busy time of year as we process and confirm the accreditation of your hours within the next few weeks. All attendees will soon receive a link to a survey to submit feedback for today's webinar, which we and our presenters highly value. So please do take a moment to complete that survey once you receive the link. Our next webinar takes place next Wednesday, April 15th, with the title Lifting Barriers, Vertical Transportation and Inclusive Access. And following that, on Thursday, April 16th, we have a risk management webinar titled Viewing Architectural Fees Through the Lenses of Scope, Value, and Risks. So please be sure to check both of those webinars out on our webpage. Again, if you are looking for additional ways to get your Con Ed hours before the end of cycle, be sure to check out the Con Ed Opportunities page on the OAA website, where we list continuing education opportunities offered by other organizations beyond the OAA. So with that, I will thank Peter once again for your excellent webinar. Thank you all for your attendance, and I hope everyone has a pleasant remainder of your day. Thanks very much.
Thanks, everybody.